This is okay to be recorded, right?
Yeah, thanks.
Okay, so our next speaker is Jain from Minnesota. So he's going to speak about who is in and who is out.
Thanks, Kevin, and thank you to the organizers for inviting me to this really great workshop. We've heard a lot about some of these themes already, virtual populations. So Tracy's talk this morning, the other Tracy's talk yesterday, and this is my take on some of my research directions using these virtual populations. We've also heard a lot about how these virtual populations can be used to simulate clinical trials, optimize treatment. And I would just like to add to that list my own motivations for these virtual or digital twins. So one is that there is a lack of patient and subject diversity in clinical and preclinical trials. So if you think about preclinical trials in mice, they're usually genetically identical animals, usually monoclonal xenografts, sometimes PDXs. The lack of minority and women representation in clinical trials of drugs has been noted many, many times by the NIH, for instance. And this all has profound impacts on success of drug, right? When the drug is even approved, does it do well or does it not? And again, in this morning's talk, we heard about drugs failing at stage 3 or whatever, phase 3 of the clinical trial process, drugs getting approved by the FDA and then turning out to not be as effective in certain populations. And then the other motivation for me is, how do we treat a given patient? And I don't only mean like optimizing treatment for that patient, but there's so many other questions that we can ask. For instance, we can try to see why an individual patient, given the way that they responded to treatment, what can we say about the tumor that was growing inside them? If the patient is in some sort of schedule, calling back to the clinic to measure biomarkers to figure out if the patient is progressing or responding to treatment or not, can these models be predictive of what the clinician can see the next time the patient shows up? So there's a lot of questions that can be asked of these sort of digital twins. And of course, this idea is new, but also at this moment, not that new. There have been a number of really nice articles that have been written about digital twins in predictive care in oncology. Just to give a brief lay of the land, by a digital twin or a digital clone, I mean basically a collection or a set of parameters that's specific to a patient or an individual. And these parameters are inputs in some sort of a predictive quantitative model. So I'm preaching to the choir here, of course. We all have our own favorite way of generating these clones or generating these virtual populations. But I sort of want to emphasize a couple of things. So I'm going to break it down into a 3-step process where in the first step, where you have to have a predictive model, right? So you need a model that's specific to the disease, the patients that or the data that you have from the clinic or the experimentalists. What's important here is that we identify parameters representative of heterogeneity. So again, this morning we saw in Tracy's talk that 5 parameters represented somehow key features of how these mice were responding to immunotherapy. So we want to identify parameters that we believe represent heterogeneity in the population or distinguish individuals. And then the question of who's in. So this is recreating through some sort of parameter estimation method the participants in the clinical trial or in the preclinical trial. So if we're talking about something like a preclinical trial, the data might be quite macroscopic, average tumor volume time courses, survival curves, but you don't really have information on individual mice. And then so there's question, what are all the possible mice that participated in that trial, or what are all the possible cell phenotypes, genotypes that participated in that in vitro trial? If we talk about clinical trials, of course, then maybe you're lucky enough and you have individual patient level data, but then how many different digital clones could that patient, could represent that patient? So it becomes a little bit a question of parameter identifiability as well. So various ways of inferring distributions on parameters. Bayesian approaches, Metropolis Hastings will allow you to sample already from the joint probability distributions on the parameters that represent these individual patients. We can also take some ad hoc methods like MLE estimation, couple that with some sort of acceptance rejection, sample importance resampling criteria, and we can generate clones of participants for which we have data. Perhaps an even more important question then is, how do we recreate participants, or how do we simulate participants that were not in that trial? How do we capture heterogeneity out there that was not represented in these experiments? And so yesterday we heard some questions about this. There was a very nice discussion. The sort of simple idea is that where the joint distribution on these parameters recreate participants that you observed, sampling independently, for instance, from marginals, might recreate populations of patients that you haven't observed, and you can sort of simulate heterogeneity. But you sort of want to do this in a really careful way. So there was again, in this discussion, this point came up: how do you know you're generating something real, or how do you validate this approach? So you have to keep in mind who you're generating their sort of biological or clinical realism. So when you simulate this virtual patient that you haven't observed and the response is completely off the charts, then maybe that's a parameter combination that should not exist, and that can inform like a joint distribution on a heterogeneous population. Is this step even valid? How do we know that when we've done this and we are getting responses which are biologically realistic, but how do we know that those people exist, or those mice exist, right? What is the validation? And then this is something that came up earlier this morning as well, energy constraints. So for instance, if some of our model parameters are representing subcellular processes, yesterday also we had a talk which spoke about the energy cost to resistance. So this is something that can be applied, that there's a certain amount of energy, ADPs, available to cells to do their usual business. And if they're going to allocate some of that energy to drug pumps, then that energy must come from somewhere. And that can give you a sort of bound on how you sample from these distributions to generate or to recreate heterogeneity. So my talk is going to be a little bit different, or the rest of my talk will be a little bit different than what we've heard. I'm not going to focus on an individual project, and this will be more like an elevator pitch. I'll talk about 3 different projects and just present you with one snapshot question from each of those that we applied this sort of technique to answering or to get insight. So I'll begin with who's in. And so this is data from collaborators at the University of Michigan's Medical Center. We have individual time courses of patient response. So these patients are prostate cancer patients. They've been put on continuous androgen deprivation therapy. And the only data we have is PSA time course measurements. So the question on this project for us was, how much can we learn about these patients if that's all that we're looking at? There's a criteria for ADT failure, and concentric circles is when that patient failed clinically. Okay, so we can write down a very complicated model, and I've done this in the past for what's going on, including subcellular signaling, antigen receptor relocalization, resistance development. How does PSA actually extravasate into the vasculature? Because it's a macromolecule, it doesn't just leak. Conditions have to be created for it to make it into the bloodstream. But instead, in this project, we adopted what I think what I would like to call Heiko's razor, which is the simplest models are sometimes the best. And this is true, like with really easy models, it's surprising the amount of insight that we can actually get, what we can actually learn. And so hopefully I'll convince you of this in this particular example. What could be simpler than exponential growth that's non-autonomous is exponential growth that's autonomous. So really, really easy model. We have a sensitive cell population, a resistant cells population. This is PSA in the bloodstream, what we are seeing over here. So sensitive cells die at a rate delta, resistant cells grow at a rate gamma on treatment. And then there's some sort of PSA expression which is normalized to initial population densities of these two cell types. And the fact that this is continuous treatment, we don't really have to worry about competition between the cells or how these resistant cells come about. So we're doing a standing variations approach that these cells, resistant cells, pre-existed, right? And so each digital clone in our model is going to be these 4 parameters. So the big picture of this project was to try to understand how much information these PSA readouts can give us, how predictive are these PSA readouts. I will give you just one example of a question that we answered. So don't worry about the picture at the moment, but the question we are answering is, supposing there is some sort of predetermined or evolving time schedule of when this patient on continuous treatment is called back to the clinic to take PSA measurements, which would be at the discretion of the treating oncologist and perhaps also of the patient and his convenience. So if we know the schedule, then we can ask this model that when will we expect this patient to fail clinically, right? Can we give the clinician some advance notice? So what you're seeing in these 2 panels is in the black stars, these are visits that have already happened, and so the model knows this data. In the light gray are all the virtual clones of that patient, given that data. In red are clinic visits that have not happened, and so the model doesn't know that data. That's when the patient failed clinically in actuality. And so even with just 2 visits after the PSA hit another, you can see there's a massive amount of variability in the prediction of what this patient is going to look like in the future. Like this is almost meaningless, right? But we can still, within between 80 to 100%, guess exactly what fraction of these clones would have failed in the clinic at that point of time. Well, at these subsequent time measurements, which is very close to what happened in the clinic. So even with this variability, we can get a very strong predictive result. And so in yellow, what you're seeing is these are all the clones that have failed ADT, predicted to have failed. In the light gray are the clones that haven't yet predicted to have met that failure criteria. And adding more data, you narrow your uncertainty in your digital clones, but that's still pretty much as good as what was before. So we thought this was quite an exciting result, again, with a really, really simple model. Okay, I'm going to switch tacks completely and move on to who's out. So that was an example of recreating digital clones of patients that we are seeing. But now this is a question of capturing heterogeneity that we haven't incorporated in these experiments. So this is very busy, but basically it's a lung cancer xenograph study. What's important is the data that was reported. It's tumor volume, average tumor volume time courses, so no individual level data, and survival curves. We are just focused on control, and then these xenographs are treated with radiation therapy. Something interesting to note is that, in fact, they did not report tumor volumes when treatment was applied. Treatment stopped, I think, in this experiment at day 5 or day 4. And then so there's no information at all on how these xenografts responded to treatment, except after the fact. So here the problem is a little bit different. We're not creating digital clones of individual mice. We're trying to figure out who are all the mice who participated in this experiment, and then who are the mice who didn't participate in this experiment. So once again, simple is good. Exponential didn't work out, so we stepped it up a notch, and we went to logistic, crazy dog. So the tumors grow logistically, and we are fitting 2 sets of data. So we also assume that the survival probability that generates the survival curves is continuous and a function of tumor size. In theory, it could be a function of animal health, captivity conditions, side effects, toxicity of the drug. In this particular example, We just went by tumor size since we had no other data to go by. So logistic growth for the tumor, and then we say the survival of these mice is a function of tumor volume. The most important thing here is this parameter rho, which is the rate at which the survival decreases for every unit increase in tumor volume. The gamma parameter, the rest of it is just sigmoidal curve. And we, of course, don't want survival to be bigger than 100% because we cannot create mice from nothing. So we can do the usual sort of Bayesian estimation. We get really nice fits to the data. We get really nice fits to the survival curve. And then so we can look at distributions of the parameters. And there's a lot that we can learn from these distributions. It turns out, I don't really have time to go through all of this, but we can connect, so we can use the model to then start predicting median times of death for each mouse that we recreated so that it matches that overall survival curve. And we can look at how the survival times for these mice depend on tumor growth parameters. And then so there's an interesting result where perhaps you can see untreated mice, survival goes down at a slower rate as a function of tumor growth rate than in the treated mice. So this is saying that after treatment, if the tumor comes back and doesn't grow down very slowly in size, then bad things are happening. I'll end with this. So the point of that whole exercise was a validation of the who's out approach. So how do we know that so we can now sample from these posterior distributions and say we've recreated mice that we didn't participate in that experiment. How do we do that? Well, we went and looked for other experiments online using the same cell line, doing the same sort of xenograph studies. So we found a paper using exactly the same cell line. These mice, the tumors grow very differently, slowly, much smaller sizes, very different survival curves. What we then did is we looked at the original heterogeneous population of mice that we generated. We said, let's look at all of the mice that we predicted would survive between this window and trace back the parameters, map it to the tumor growth volume, and that's like magic. So we are recreating, this population exists. It sort of validates the who's out sort of experiment that we did. So this was a really exciting result, we thought. Am I pretty much out of time? Okay, so I'm gonna skip over all of the rest of this and end with a shameless plug for some of the stuff that Tracy was talking about yesterday morning about parameterizing ABMs. It's a completely different topic. Thanks.
Thank you.